Okay, in this video I'd like to introduce the concept of partial pressures. And partial pressures is a useful concept when we're dealing with mixtures of gases. And very often we do have a mixture of gases. So for example, if you were running a chemical reaction and generating a gas as a product, but the product was being generated from two solutions reacting together, two aqueous solutions, you might also have water vapor as another gas. The water vapor is not a product of the reaction, but it is present. And so that would end up generating a mixture of gases, even though the water was not part of the chemical reaction. So it's very helpful to be able to talk about partial pressures when we're dealing with gas mixtures. So first of all, let's talk about what partial pressures are. So when you have a mixture of a gas, when two or more gases are placed in a container together, each gas behaves, and we're going to assume for a moment that these are ideal gases. Each gas behaves as if it were alone by itself. Now, what does this mean for a gas to behave alone by itself? Well, remember that when we had a container of gases, that I could imagine that if I had one gas in there, that one gas was going to spread out to occupy the whole container, right? As if it were the only gas in the container. But if I had another gas in the container, it would do exactly the same thing. It would also spread out to occupy the whole container. So that's what we mean by they act as if they were alone by themselves. They occupy the whole container, each of the individual gases. Each of the individual gases is still going to be colliding with the sidewall of the container. And as they do that, they are going to be generating their own pressure against the sidewall of the container. Well, in this example, if the gas that I've represented in green is colliding with the sidewall of the container and creating a pressure, and the gas that I've represented in red is also colliding with the sidewall of the container and generating a pressure, then the pressure exerted by the green gas can be added to the pressure that is exerted by the red gas, and so the total pressure in this container is the sum of all of the pressures of the individual gases. So that's what we mean by partial pressures. The pressures exerted by each gas are additive. We add them all up to get the total pressure in the container. And this is Dalton's law of partial pressures. The total pressure in a container equals the sum of all of the partial pressures. So the way that we represent that is we say the pressure exerted from gas A plus the pressure exerted from gas B plus the pressure exerted from gas C, and so on for as many gases as we have in there. This is Dalton's law of partial pressures. The total pressure that is being exerted on the sidewall of that container equals all of the individual or partial pressures, the pressures due to each of the individual gases. So Dalton's law of partial pressures can be very useful for when we are trying to find or solve for one of the properties of a gas when it is in a mixture. So let's take a look at a couple sample problems here. I'm giving you a sample problem. What is the total pressure? So I'm looking for P total. What is the total pressure exerted by 1.5 moles of N2 gas and 2.0 moles of O2 gas in a 5.0 liter vessel? There's the overall volume at 15.0 degrees Celsius, and that is a temperature. Remember, that temperature is going to have to be converted to kelvins, right? So first of all, we know that we're looking for the total pressure, and the total pressure of this system, according to Dalton's law, is going to be the added partial pressures of each gas, the added pressures from each gas. So the total pressure is going to be the pressure due to the N2 gas plus the pressure of the O2 gas. So using Dalton's law, if I can find out what the pressure of the nitrogen gas is and the pressure of the O2 gas, oxygen gas, is, I can add them together and get the total pressure in this 5.0 liter vessel. A vessel is just another word for a container. So I'm going to first calculate the pressure exerted just by the nitrogen gas, its partial pressure. And I can see that it's 1.5 moles of it. I'm given the number of moles of gas. I know the volume that it occupies. I know the temperature that it's at. And I'm asked for pressure. Which equation am I going to use? If I'm given volume and temperature and moles, which equation can I use to calculate the pressure? It's going to be the ideal gas law, isn't it? So I'm going to use the PV equals nRT. And I'm calculating the pressure, so I need pressure alone by itself. So pressure alone by itself, I need to divide both sides by V to get rid of V. So pressure equals nRT over V. Well, let me start plugging this in. This is for nitrogen, right? For N2. So for nitrogen, pressure equals nRT over V. So what is N? 1.5 moles. What is R? It's the gas constant. What is temperature? It must be in kelvins, so I'm going to have to convert that to kelvins. 15.0 degrees Celsius. 15.0 plus 273.15 is 288.15. I can only go out one place past the decimal, so that 1 becomes a 2. So that's 288.2 kelvins. That's my temperature. Divided by the volume. What is the volume? Well, remember that this nitrogen gas is going to completely occupy the whole volume space as if it were alone by itself, and the whole volume is 5.0 liters. So there I have plugged in everything, and that is going to give me my pressure specifically of the nitrogen gas. So the pressure of the N2 gas equals, let me do this math on my calculator, and rounding to 2 sig figs, I have 7.1, and the pressure is going to be in atmospheres. So that is the pressure exerted just by the nitrogen gas. This is also called the partial pressure of the nitrogen gas. Okay? So I now know that value right there. Remember, I'm trying to solve for the total pressure in this vessel. I now know that value right there. So what I would like for you to do in this problem is I would like for you to carry it through the rest of the problem, steps B and C. So you're going to do the similar thing that we did here for nitrogen. You're going to do it for oxygen to calculate the partial pressure of oxygen. And then you're going to add those two partial pressures together, and you'll get the total pressure in the vessel. So go ahead and pause the video and complete this whole problem all the way through step C. All right, coming back from pausing the video, we are now going to work on the O2 gas, and we're going to calculate the pressure. So we're going to use our ideal gas law, PV equals nRT, assuming that these are ideal gases, that they behave in an ideal manner. I'm solving for pressure, so I need to get pressure by itself. So P equals nRT over V. And now I'm going to plug in the values. N, the number of moles of the oxygen gas. How many moles of oxygen gas are there? Well, I can go back up here and I can see in the problem, they told me that there were 2.0 moles of oxygen gas. So that's what I'm going to put in here. 2.0 moles of O2 gas. R is my gas constant, 0.006 liter atmospheres, moles kelvins. And temperature is my temperature in kelvins, and I've already done that calculation. It's right up here, 288.2 kelvins. Okay, and then all over the volume, which is the volume of the whole container, which is 5.0 liters. So if I do this math, I'm going to get an answer, and I need to round it to 2 sig figs, and that's 9.5 atmospheres, and that is the partial pressure of the O2 gas equals 9.5 atmospheres. There's my answer. So now I have the partial pressures of my two gases. The partial pressure of the N2 is exerting 7.1 atmospheres of pressure, and the partial pressure of the O2 gas is 9.5 atmospheres, and Dalton's law says that the total pressure in the vessel equals the sum of all of the partial pressures of the individual gases. So here I go, Dalton's law. Total pressure in the vessel equals the pressure from the nitrogen gas plus the partial pressure from the oxygen gas. So I'm going to plug in those values. Partial pressure for the nitrogen gas was 7.1 atmospheres. Partial pressure from the oxygen gas was 9.5 atmospheres. And so the total pressure in the vessel is 7.1 plus 9.5, or 16.6 atmospheres of pressure total. And that's how we can use Dalton's law. Again, Dalton's law says that the total pressure in a vessel is just the sum of all of the individual pressures of the individual gases in the mixture. So to find the total pressure of a gas, we can just find the individual pressures of each gas and then add them all together, and we can get the total pressure in the container. So there are a lot of different ways that we could manipulate Dalton's law. Let's say, for example, you were given the total pressure and the partial pressure of one of the gases, then you could figure out the partial pressure of the other gas. So we're kind of working backward in that regard. And once you got the partial pressure of one gas, then you could figure out how many moles of gas you had by plugging that partial pressure into the gas law. Or you could figure out the temperature or some other variable in the ideal gas law. So we can work forward and backward using Dalton's law. Okay.